Okay, so today is going to be our last day where we are doing the same thing that 401 is doing, right? And so we're basically finishing up learning how to program in Java, just kind of the basics, and then where 401 is going to go off and kind of talk about object-oriented programming and the craft of programming. We're going to kind of dive down a little bit and talk a little bit more theoretically, a little bit more rigorously, and start to get into the data structure stuff. So today in particular, I'm going to go fairly fast because I really want to get past all of today so that we can start on Thursday and be past all this. So there's a couple of example codes, examples in the lecture code that I'm going to skip or kind of go over fairly quickly. But basically what we have so far in terms of what we've done is essentially program in Java without using any object-oriented kind of techniques at all, without really thinking about objects, how to create objects. Now for us in this class, we're going to think about objects as data structures. And then we're going to go off and talk about data structures and reason rigorously about data structures. But up to now, what we've done is basically 110 level programming where we've programmed with static methods. These are basically methods that are available when our program starts via the class name, and put all of our methods into one big class, and we start in main, and that's it. We've kind of learned about the atoms of programming, right? For loop and while loop and variable declaration, and then created a mental model for the computation. So we reviewed environment diagrams and the stack and the heap and how that goes. So what we're going to do today is we're going to talk about why we need data structures, why we need to be able to take multiple pieces of data and glue them into a new piece of data that we can reason about as a whole. Now, in an object-oriented programming language like Java, this is also going to be called an object. You can think of data structures as objects because objects are data structures. Now, when we start talking about data structures, we're going to start talking about them very rigorously and be able to talk about proving things about them or be able to reason about them. And so it'll be less about just programming with them and more about understanding them a little bit more deeply. But we still need to know how in Java we can create a structure, how we create an object. And even why, right? Like to motivate why it is that we want to be able to take multiple pieces of data and kind of glue them together into a structure. So toward that end, what we're going to do is, oh, shit. So you can't see anything because nothing is on the screen. What the hell? All right, well, this might be a problem. Let's try this one. Oh, I wonder. Is it blank? Aha! What about? OK. So what we're going to do is we're going to develop a program that I'm calling Triangle Area App. And we're going to write it in a non-object-oriented way, right? We're just going to use static methods like we've been doing, just 110 level programming, and then kind of step back and take a look at exactly what these different pieces of information are doing in our program and how we can recognize how some of them really belong together in some sort of structure, in some sort of object. I'm basically going to do the very first part of the example and then skip all the way to the end and do the last part of the example because this next 4 or 5 steps is simply building up this program one thing at a time. And so there should be relatively nothing new, right? So the idea behind this program is it's going to be a simple input-output kind of thing. We're going to take in input from the scanner, and we're going to process it. And what we're going to do is we're going to expect our data to be given to us in the following format. We're going to have a series of triangle definitions. And a triangle definition is going to be a single word that is a name for the triangle, followed by 6 numbers. And these 6 numbers are going to represent coordinates in kind of your xy plane, an x coordinate and a y coordinate for 3 points, right? 3 points make a triangle. 2 coordinates make a point, and you can kind of see where we're going to go with this. But these 6 pieces of information, these 6 numbers, are essentially going to be the definition of our triangle. And as we build this program, we're going to write little helper applications that are helper functions that are going to be able to tell us or help us calculate different pieces of information about our triangle. In particular, we're going to categorize our triangle by whether they're equilateral or isosceles or scaling. We're going to calculate the areas of these triangles. We're going to keep track of the average we're going to calculate the average area for the different triangles by category. And we're also going to keep track of which triangle is the smallest one. That's, that's what our program will do, right? So let's start off. And like I said, I'm gonna do the version 1 of this, and then I could probably skip all the way to version 5 of this, just because everything between 1 and 5 is really just building up this program one step at a time. And so it shouldn't be terribly surprising. So we'll start off with version 1 of this application, where all we're doing is reading in the numbers and making sure that we're reading in the numbers correctly, and kind of creating a skeleton for our application. Right? So going to the code. Here is our program to start off with, right? Relatively simple. It's all one method. It's all just in main. And we start off and we create a new scanner, right? And this is we've done before. It's boilerplate. We're starting to learn a little bit about what these things that we just took as boilerplate before. Now we kind of can understand them a little bit. We understand that new keyword is creating a new object on the heap. And we haven't really talked about the how to use the new keyword. We will today. But the idea being is that we get this scanner object. And we've used a few objects. We used the scanner object. We used strings. We used arrays. But we haven't really talked about how to construct or define our own new objects, right? So we create a scanner object. And basically, while the scanner still has another word to process, we're going to read in that word as the ID for the next triangle. And if that ID happens to be end, we know we're at the end of our input and we're done. And we're going to break out of our loop. A couple things to point out here. The use of equals to compare two strings. We never compare two strings with a double equals operator. And also the use of the break keyword for breaking out of our while loop, right? So great. So we read in a triangle name. If the triangle name is not end, we know that this is the next triangle. And so then we know the next 6 things on our input are going to be double numbers. And so we're reading those in and storing them in these local variables, ax, ay, bx, by, cx, and cy. And in this very first version of the of our program, all we're going to do is just print out what we have, right? Just to make sure that we have a basic skeleton of an application working. And if we run this, right? And we say, oh, triangle A starts at 1, 1, goes to 2, 2, and then goes to, I don't know, 56.7, 123.5. It's a weird triangle. That's fine. Yep. Our while loop seems to be working. Things we can keep going and put in new numbers, right? And we get a different triangle, et cetera, until we finally type in end, and then our program ends, right? So basic, right, kind of core while loop, just processing input. We're able to confirm that the input is read in the way we think it is. Okay. So now let's go on to the next part of what we want. We want to categorize our triangles by their side lengths, right? As either equilateral, isosceles, or scaling, and then report that triangle's category for each triangle. So let's go ahead and do that. So we can update the next version of our application, right? I've commented out where I print out the information because that was just for a little test. And now we're gonna do what we want to do, which is to print out the category of each triangle. That's the first thing our program wanted to do, right? And so we need to calculate what category our triangle is in. It's either going to be equilateral or isosceles or scaling, depending on the side lengths. And here, I can when I'm programming, I often come to a point where I know I need to compute some value and that there's going to be some work involved in computing this value. I often will just pretend magically that I've written that method already, and then just pretend I've wrote it, saying, oh, if I give it these pieces of information, it should be able to give me back some other the thing I need, and so that lets me kind of concentrate on the main program I'm writing, and then later on I can go back and identify all of these methods I just kind of made up out of my head and like go off and program each of those carefully and individually to do what I envision them doing. So in this case here, I envision that we're going to have a helper method called triangle category that can take the data associated with our triangle and compute one of these 3 triangle category labels. And if I look at what such a helper function might look like, right? Here's a static string. It's going to produce a string. It's called triangle category. It's going to take in these 6 numbers. And so I do this again, right? I say, oh, what I really want to do is calculate the distance between the A and the B point, the B and the C point, the C and the A point, and then compare them in some way and then categorize my triangle. Well, I know that I'm going to calculate the distance between these points using the numbers that represent the points. And so I imagine maybe, I have some point distance method. And so I go ahead and just kind of use it without actually, or create it kind of, while I need it or when I need it, without having actually written it first, right? So this is a bit of a top-down programming. Wherever you get to a point where you're going to have to do a whole bunch of work in order to arrive at some calculation or to come to some conclusion or to affect some change, you can kind of pretend that some method exists that does that work for you, and just keep programming the larger idea of your program, knowing that you can go back and fill in these helper applications. So in this case, I might say, well, I'm going to assume I have some point distance formula that's in some method called point distance that can take in the 4 numbers that are associated with 2 points and come back with the distance between those points. And so I calculate side AB, side BC, and side CA, and now here's the work of categorizing the triangle and I basically are comparing these sides to each other in order to decide which category I'm in, and I return the appropriate category label. So finally, the last bit is, well, we need to provide the helper method for calculating point distance. So that one's actually just a one-liner. And here it's just the point distance formula, right? x1 minus x2 times x1 minus x2. So the differences in x's squared plus the differences in y's squared. And then all of that sent to the square root function, which is a static function inside my math class, which is a standard library for calculating square root. And I return that, right? OK, so there's something I've done in triangle category specifically, which I told you not to do, right? And so I'm going to give you just a few moments to confer with your neighbor if you'd like, and try to figure out on what line have I done something that I really am not supposed to do, right? Or what is wrong with my triangle category method. All right, so go ahead and try to figure that out for just a bit. All right, who thinks they know where the problem is? There's only like, what? 9 lines in that entire method that have anything on them. So just choose a number that has something on them. How about that? You have 1 in 10 chance. Right.
Is it where you didn't check both sides are different to return scaling?
No, so they do, well, that's a logical thing, right? If it's not equilateral and it's not isosceles, then it kind of has to be scaling. So that's not the problem.
47?
47. Yeah, returning isosceles is OK. Did I misspell it? No, all right. Good guess, though. There we go. There you go, right. So you might remember I kind of made a big deal about not comparing real values using equal, like the double equal operator, because real values, remember, are subject to round-off error and numerical, and kind of numerical error as a result of the fact that they represent real values, right? And so, so when you're trying to compare 2 real values, you really must decide on what the appropriate epsilon bound is for your domain, for your program, for what you're trying to do. And if you need to compare two real values for equality, or any relation that involves equality, less than or equal to, greater than or equal to, then you need, for the equal part, right, you need to essentially decide how close is close enough, subtract the two values, take its absolute value and compare that against your threshold, right, your epsilon bound. And so, so that's the issue here. We really shouldn't be comparing with double equals. Now, it's going to work in some cases, but it might not always work, and that's the point. And that is actually, where lots of errors get introduced. So like if I press play and just play around with it, and I say, OK, triangle A is going to be from 1.0 to 1.0 to, let's say, 2.0. 2.0 and then to 3.0 back down to 1.0, right? Then it's going to recognize that as an isosceles triangle. So clearly, the double equals operator, when it compared the two sides that are equal, worked, right? In this particular case. The problem is it's not always going to work, in particular, depending on how you've calculated your double value and comparing it to some other double value. You could get very, very close without quite being the same. But for your purposes, you want them to be the same. And so that's why we need to have that epsilon bounds. So sometimes it'll work, sometimes it won't work, but that's OK. I just want to use that example to kind of point out what not to do. Now, we can fix the example later. In the very, very last version of the example, it is fixed. And we're not going to fix it now. But that's, just wanted something to point out here. OK. Now, the rest of this is going to, basically keep adding to this program, doing additional things that we want to do until we finally get to the full version. And so what I'm going to do is I'm going to kind of skip to the full version, right? So version 3 reports the average size of triangles by category, and version 4 reports the area of the smallest triangle, right? And so now, I'm going to jump straight to version 4. We'll review it really quickly and see what we added, and then we'll really get to the meat of what we really care about, which is taking a step back and looking at this program with fresh eyes, from a perspective of where we need a data structure, right? OK, so skipping to version 4 that has our full program in it, right? It looks something like this, right? I've added some local variables here for keeping track of the sum of the areas for each category and how many triangles were in each category. I've added some variables here for keeping track of which triangle is the smallest in my while loop, right? I've capture what the category is and then print that information out. I capture what the area is. And so just like we had a helper function that calculated our triangle category, we have a helper function that calculates our triangle area. And if we look at that triangle area function, it looks something like this, right here, right? Where, again, we take in the information we need to know about the triangle, all the coordinates. In this case, it's a lot like the category area, function in that it calculates 3 sides and then returns a formula, right? Returns the area calculated from the 3 side lengths. I can't remember, the name of this formula. I'm sure it has a name. Somebody in here, I'm sure knows it. But it's right. Trust me. So that's the formula for taking 3 side lengths and turning it into a triangle area, and we return the triangle area. And just like triangle category, we gave it some information and we got back the triangle category. Here, triangle area, we gave it the information about the triangle and got back the triangle area, right? And right, so then so that allows me to calculate the triangle area. In terms of keeping track of the smallest, right? This is something you often have to do, is you have to loop through some array or some list or some structure of some sort, some collection, and you're basically scanning that collection of things for something that is the smallest or the largest or the most northeastern or whatever, right? And so you're constantly keeping track of the one you've previously found and comparing comparing each one to the one you've previously found, and if it matches the criteria better, replacing the one that you've previously found. It's a very common idiom, right? I just wanted to point out one thing about how we might do this. One way to do this is to, for example, keep local variables for keeping track of, in this case, the smallest triangle, and use a special value in order to know that you haven't found one yet. Right? And because the thing is that when you're doing that kind of scanning through a collection, the very first thing you examine is by definition the smallest triangle, right? And so there's nothing to compare. And then every other triangle after that, you need to compare to the previously found smallest triangle. So you still need to find some way of distinguishing that first time. So one common way to do this is to use a special value that you can detect as that's only going to be there the first time through. So here, the string that this smallest ID name, variable name, I've set to null. I've initialized to null, and this is supposed to be the name, right? The label for the smallest triangle I've found so far. So I can use the fact that smallest ID is null to know that I really haven't. This must be my first time through the loop. And because I have that special value as null, it doesn't really matter what I say for smallest area. I can set that to 0, and I'm good, right? Now, if I didn't have the smallest name, if I only had smallest area, then I couldn't use 0 as my smallest area because, how about if I had, well, I guess you could, because you could say that no triangle will have 0 area. But the point is that it's harder, right? Maybe I'd have to choose a negative number, something I can detect as being kind of just wrong, right? So the first time through my while loop, the first thing, when I get to the point where I'm trying to keep track of the smallest, here I check to see, is my smallest ID null, right? If that's the case, then I know, this must be the first time through the while loop, and I'll just go ahead and copy the area that I've calculated to the smallest area, and and I'll go ahead and take the ID of the first triangle as my smallest ID, right? Set that string. And I know that now that I've set smallest ID to be something, in this case the name of the first triangle, that the next time through the while loop, smallest ID won't be null, and I won't go back into here. Instead, I'll go to this part where I actually compare the area of the current triangle against the smallest area, and then update it only if it is smaller, right? That's one way to do it, and that's a perfectly reasonable way to do it. Personally, I prefer the use of a Boolean flag in order to keep track of this explicitly. I just think it's cleaner. I think it's more expressive. I think somebody reading your code can tell what's going on. So the way I would normally program this would be to add one more flag as a local variable that I initially set to true, basically a first time flag, and then rewrite this little piece of code more like this. Right? Where I explicitly ask, is this my first time? If it is, then, well, it's no longer going to be my first time next time. So go ahead and set that flag to false, and then copy the area and the ID to my tracking variables. And then the next time through, first time will be false. And so then I can check to see whether the area is actually smaller than what I've seen so far, and only update those tracking variables as necessary. Not a huge point here. These are equivalent pieces of code. I'm just kind of showing you two ways to skin that same cat. Personally, I think that if instead of relying on special values and kind of somebody understanding how you're using that special value as this indicator that this is the first time through your while loop, I think it's just easier to and a little bit more easy to read if you just use a Boolean flag, which keeps track. Is this my first time or not? Right? In any case, right, we go through, we find the sums of all the areas by category and keep an account of by category. We keep track of the smallest thing, and then we print out our information. And I'm not going to bother running it. You can run the code and play with it all you want. All I really want to do here is just set up this example in order to give us a context for the discussion that's to come, right? In particular, right, let's think about this non-object-oriented approach of writing this program, right? So what did we do? Well, all our functions are static, right? So we just had our main function that was static. We created some helper functions along the way. We just threw those in the same class and made those static too. We didn't define any new abstractions. We didn't create any data structures really, or otherwise reason about our program in any higher order way. We just kind of programmed it in a very straightforward manner, right? Which is fine, right? All the variables we use, all the names we use, are either local variables or parameters for all these static methods that we defined and used, right? And these static class functions that we're creating as helper functions, essentially, if you think about it, are acting as a library of triangle-related functions used by our application, right? So if we look at what kind of helper functions we ended up with, triangle category, triangle area, point distance, right? These are all triangle-related methods that says, oh, okay, you give me this information that is related to a triangle, and I give you back different information, or some property of that triangle, or some calculation that I've calculated on that triangle, right? And if we wanted to reuse these methods in lots of programs, if we wanted to use them in different programs rather than this just one program, one thing we might think about doing is collecting all of these static helper functions that deal with the triangle, putting them in their own class, so that we can write lots of programs and just go to that class and use these static methods as we need. And that really is how we used to program before object-oriented languages came about, right? So we would, we would recognize that, there are things that I want to do with triangles that, I not only need to do with this program, but I'm going to want to do some other program and some other program. So it's better for me to create a library of triangle-related functions, document that library so that somebody else can, including myself, can then use that library in the service of some program. So we might have some library of triangle functions, and it says triangle category, given 6 points, given the XY coordinates of the 3 points of a triangle, will come back with a string label that categorizes the triangle, or triangle area, or triangle whatever, right? And so, and then we hopefully we don't even have to build up libraries of our own. Hopefully other people have written libraries, and so when we want to go off and write some new program or some new system, we find I'm going to write some program that's going to do some polygonal model thing, and needs to be able to do some manipulate triangles. And it's like, oh, here's a library written by somebody who manipulates triangles, right? And so I go and I read the documentation, learn how to use the library, and then whenever I need some triangle-related function, I call that triangle-related function as appropriate. And that's fine, right? I mean, that works. But there's a problem with that, right? And the problem is that essentially, if we think about the role of what we pass to those triangle-related functions, right? When we said triangle category, we needed to give it the information about the triangle that it needed in order to then calculate the appropriate category. In this case, this particular helper function, this triangle category function, says, you give me a description of a triangle as 6 numbers, right? The first 2 numbers being the x and y coordinate of one point, the next 2 numbers being the x and y coordinate of the second point, and the next 2 numbers being the x and y coordinate of the third point. You give me those 6 numbers, and then I will give you back a string which is appropriate for the triangle that those 6 numbers describe. So there's an implicit kind of sense that these 6 numbers are the triangle, or at least the part of the triangle we need to know for that helper function to do its job, right? So collectively, those 6 numbers represent the triangle, and for me to use those 6 numbers with my helper functions or my library of triangle functions, right? The onus is on me to understand how, as a programmer, how those numbers are supposed to be given to those helper functions, right? Is it the AX, then the BX, then the CX, followed by the AY, the BY, and the CY? No, that's not true. That's actually not how it is. It's really the AX followed by the AY, and the BX followed by the BY. So, in addition to giving the information, I need to know, how to give it. I have to understand, the documentation for the function for which numbers are provided in what order and why, right? And so that's fine. That's okay, right? I mean, but there's this notion that those 6 numbers represent a triangle. It's not just any 6 numbers. I didn't pull these things out of thin air. But that notion's in my head, right? I know that those 6 numbers represent the triangle, and therefore I can provide them to this triangle-related function in order to get back some reasonable answer, right? And I can do things to make it so that other people reading my code also know, like, for example, I can use descriptive variable names like AX and AY and BX and BY, suggesting this first number is the X coordinate of the A point, this second number is the Y coordinate of the A point, right? But it's still very implicit, right? It's not like, they're still just 6 numbers, right? And there's just 6 variable names. And if I went back through and I changed those variable names to be banana and slug, and table and chair, right? The program would still work, right? Now, it wouldn't read particularly well, but it would still work, right? But this idea that the programmer holds in their head the relationship between different pieces of data and what it really means with respect to some helper function or some library of functions or some idea that the programmer is trying to manipulate, right? Was kind of the state of the world before we came up with object-oriented programming, right? But as we had experience with programming, we kind of realized, what we really need is a language or a set of languages or new languages which allow us to more rigorously and formally glue pieces together as a structure and say these things are a triangle collectively. In order to relieve the programmer of having to constantly maintain that model internally and then use it correctly, we want to be able to express that idea that these numbers belong together in a particular way for a particular purpose. And that is what, at first, that idea was embodied by simple data structures and non-object-oriented programming languages like C. And then later, we invented entire programming languages kind of centered on that idea, that we're going to have the language features, the idea of the language is to allow us to define these kinds of software objects, these abstractions, and work with them, right? That's going to be the primary way we program, and therefore, we want to create a language with features to support that, that notion. And that's object-oriented programming, basically. So object-oriented programming flips the relationship around. It basically says, oh, it's not that the programmer has to know what information to pass the function in order to then get back the right answer. Instead, we take the information and we glue it together into a structure, and then we define the manipulations and the behavior of that structure as part of that structure. So then once I've created the object, now I don't have to know anything about what information is stored and how it's stored and what means what. It just provides me with a interface, right, that allows me to manipulate it and work with it and query it for its various properties without having to know, what the data is and have to pass that data into those functions. Those functions are now defined as part of having glued them together, right? And that idea of creating abstractions and then providing behavior for instances of the abstraction, right? That's object-oriented programming. So how do we do that in Java, right? Well, the first thing to do is to name the abstraction, to think about what it is you're trying to represent and give it a name. Right? So in this case, it's pretty easy. It's pretty obvious. The thing we're trying to, our program wants to work with and manipulate and otherwise, use are triangles, right? And so if we have, the abstraction, the idea is we want something to represent a triangle. And so once we know that and we have a name for it, triangle, then we create a class for it, right? And so here is where we're really going to start getting into more Java-esque programming rather than using Java in this kind of weird, brain-dead way with just static methods. We're actually going to use Java the way it's supposed to be used. So yes, we still have a main class with a main method, but that is static, and that's where a program begins. But usually in Java programs, the main method is the only thing in that class, and it's just there to be the starting point for the program. Then the actual work of the program is going to be creating and working with instances, with objects of that are defined in other classes. Usually a class is all about defining an object. There's no main in there. There's no actual program in there. It's really there in order to define an abstraction, which then gets used by some main program. So in this case here, what's the abstraction that we want to create? We want to create an abstraction for a triangle. We want something to represent a triangle. So triangle is the thing that we're trying to create, right? Create an object for. And so we're going to create a class named triangle. All right, so let's go ahead and do that. If we go to version 5 here, right? So here's our original application. I'm just going to leave that alone for now. But let's look into triangle. So here it is. Public class triangle, open curly brace, close curly brace. Voila! We've created a class for triangles. Now, it's empty. We haven't done anything with it. It doesn't do anything. It doesn't hold any data. It doesn't define any methods. But at least we've created it, right? We know now that this is going to be the thing that is a triangle, right? So the second step, once I've named the abstraction and created the class, is to declare its fields, right? Now, we haven't talked a lot about fields. We've talked about variable names, local variables, and parameters. Those are on the call stack, right? That's our little scratch pad, our little table of what names are available to me in my method. And we now know how function. And when we call a method to another method, we get a new call frame with our new variable names for that new method invocation, and the idea that some of those names refer to structures in memory, like strings or arrays, right? We saw all that over the last couple of days. And so those are just local variable names, and parameter names. We've encountered fields just in a few different places. One, we said, length. The length field of an array, right? And we said, if you have an array structure, you have a reference to an array, you can get to its length by going through that reference with the dot operator and asking for its length field, right? And we said, that's the size of the array. So a field is data associated with a class or object. You can have static fields. Those are associated with the class as a whole. And you can have instance fields. These is data associated with a structure, with a particular object. So arrays have a field associated with them called length. And I can, given a reference to an array, I can go through that reference and ask for the value of that length field. Now what we're going to do is we're going to start designing and building our own structures, our own objects. So here we need to decide what are the fields, what are the data, what is the information that needs to go into a triangle. Well, we already know this, right? It's those 6 numbers. But this is the point where we start to make choices about how we're going to implement this abstraction, right? So this is not the only way to necessarily define a triangle. We could define a triangle as, 2 side lengths and an angle, right? Or possibly, or I guess that's not quite enough. There are many different ways to specify a triangle other than the XY coordinates of its endpoints. But we made decisions at this point. We decide, okay, for this implementation of this abstraction, what is it that we're going to store to make part of this abstraction? And in this case here, we're going to say, it's going to be 6 real numbers. And they're going to represent the x and y coordinates of 3 different points. All right, so how do I do that in code? How do I tell the triangle class, hey, every triangle is going to have 6 numbers? Well, I declare the fields in the class body, right? And they look a lot like normal variable name declarations, but they're not inside a method. It's not a local variable. These things are going to be floating outside of the method, just inside the class body by themselves. So any what looks like a variable name that's floating inside a class body that's not part of a method isn't really a local variable. What it really is a field, an instance field, right? And so even though you can put them anywhere, and you can put them between methods and at the top and at the bottom and out of order and in between comments or whatever, it would be annoying to read your code if you've hidden your fields inside, in odd places. Generally, the convention is you take all your field declarations and you put them at the top of the class, right? And so that would look something like this. Okay? So here's my triangle, right? And every triangle is going to have 6 fields. And those fields are going to be called AX, AY, BX, BY, CX, and CY. That doesn't mean that there are 6 variable names that have values. No. It means that every triangle has 6 fields. That means if I have 2 different triangles, they have their own fields. So triangle A will have values for AX through, AX, et cetera, all the field names that are associated with triangle A. A different triangle in memory, triangle B, will have a different set of values. The way I get to these values is the same, though. I start with a reference to a triangle, right? And then I use the dot operator and then the field name. So I need first to create a triangle and have a reference to it, right? So creating a triangle creates this structure in memory in heap, and the reference to it, that's how I can, hold on to it and manipulate it and otherwise refer to it, right? Just like my reference to an array or my reference to a string, right? And then in my program, if I have a reference to a triangle, I can get to its field values through that reference by using the dot operator and then the field name. But what I haven't done, so that's great. We can do that. But right now, we can't actually do that because we can't create a triangle, right? We have no way of creating a triangle, right? So once we defined what is going to go into a triangle, like what fields I need, and we also, of course, have to choose what type that information is, then we need to be able to provide a way of creating a new instance of this abstraction. So that's step 3, which is defining a constructor. So a constructor is, it looks a lot like a method, but it's not a method. It's a special method, if you will, that has one job. And that job is to create and initialize a new instance of the abstraction, right? So you use a constructor with the new keyword. You have to say new and then something, right? And so that something is a class name. And so then when you say new triangle, it's going to go into the triangle class, and it's going to look for a constructor, a special method that the new operator knows, that's how I'm going to initialize this new object. So the new operator will first create the actual object in memory. It'll allocate the space for it, right? It'll create the reference, and then it's going to find the constructor in the class the defined constructor in the class, and then it's going to execute that constructor, providing that constructor access to this new object in memory so that the constructor can fill the fields with the appropriate values. That constructor may require information to be provided to it, right? So just like we can provide information to a method so that it can do its job via parameters, we can provide, hold on. I'm trying to sneeze. All right, so we can provide information to a constructor through parameters to the constructor so that it can do its job. Right, so any information needed by the constructor needs to be passed in as values, parameter values to the constructor. Right. So let's get an example so we can see exactly how this works. So in version 7, I'm going to create a constructor for my triangle, right? So here are my fields in my triangle, and here is my constructor. Now it looks a lot like a method, but it's not a method, right? Or you can think of it as a method, but a very special method. In particular, we don't declare it quite the same as a regular method. Remember, a method declaration had a whole bunch of parts, right? The first thing it had was its access modifier, where it was public, private, protected, or whatever, and we basically said, we'll just deal with that later. We're not going to use access modifiers. But they do, they essentially access modifiers will affect where this method can be used. Can it be used only in this class? Can it be used in this package? Can it be used anywhere, etc. Right? Same thing for a constructor. The constructor, like a method, will also have an access modifier that will affect where this constructor can be used, like where code can be placed that creates a new triangle. So, can it be anywhere in any package of any, other class? Can they use it, or it has to be only in this package, or can it only be in this class? Wherever, right? So, until we know a little bit more better, we'll assume that all of our constructors are always going to be public, because we want this abstraction to be able to be used anywhere, right? So we want anybody to be able to create a new triangle, and so we're going to mark our constructor as public. We'll find reasons not to later, but for now we'll just say everything's public. So our constructor is public. Just like methods have an access modifier, constructors have an access modifier, and in this case we're just going to choose public. The other thing that a method had, remember, was static or not static, and this is now going to come into play. But up to now, we've always used static methods. And that means that the method belonged to the class as a whole. Didn't matter whether we had an object or not. We could just use the class name in order to get to that method. So, for example, all of those static methods that are defined in the math class, so that we can get to math.square root and math.power and math.exponent and math. Whatever, right? And so that's fine, right? That's a perfectly reasonable use of static methods as related to some class, but being able to use just using the class name. In this case, a constructor is specific to, is not a, there's no static constructor. So unlike methods, there's no possible static keyword in front of a constructor, because a constructor is not related to the class as a whole. The constructor, like instance methods, which we'll see in a second, is related to a specific triangle. So when things are related to a specific triangle, you don't have the static keyword. So we don't have the static keyword in front of our fields, because this is not information related to this class as a whole. This is information that's related to a specific triangle. We don't have a static keyword in front of our constructor, because we're not constructing, the constructor isn't for the class as a whole. The constructor is for a specific triangle. So not having static in front of a method says that this method only makes sense in front of, in terms of a specific triangle, and not for the class as a whole, right? So we don't have the static keyword. The next thing that we usually have in a method that we won't have in a constructor is a return type. A method returns a value, possibly, and needs to tell what kind of value it returns. A constructor doesn't return a value. Like, there's no possibility for a constructor to return a value, because the constructor's job is to initialize a new object. And that's the only job a constructor has. And the result of the new operator is a reference to that new object. So there is no return value for a constructor. And because there's no return value, there's no return type. So we don't see that in there as well. Then the next thing that's usually in a method is the method's name. In this case, we do have a name for the constructor, but it can't just be anything. The way we know it's a constructor is because the name of the constructor must match the name of the class exactly. So this is the triangle class, And therefore, this is the triangle constructor. And in fact, that's how we know it's a constructor, right? I mean, if it had some other name, then it would be just some normal method. And then, if I put some random text here, now it's going to complain because it's like, hey, this method doesn't have a return type. And they're right. If this was just a normal method, it would need a return type. But because it matches the name of the class, it gets recognized as a constructor. Just like methods can have parameters given to them, so can constructors, and that's the same. So here, this particular constructor says, I can initialize a triangle for you, but you need to give me some information to do it. And the information you need to give me are 6 numbers. X1, a Y1, an X2, a Y2, an X3, and a Y3, right? So declaring a constructor is a lot like declaring a method with just a few differences. Almost always public, never have a return type. The name is always going to be match the class name, right. Otherwise, the body of the constructor is code just like a method, right? What happens when I ask for a new triangle is the new operator will first construct will allocate the memory for the structure in the heap, right? And create a reference to that structure. And then it will execute the matching constructor, right? And when it executes the matching constructor, it sets up a special keyword called this that refers to the specific triangle that this constructor is supposed to initialize. And we'll see that that's the same thing for instance methods. For instance methods and constructors, when they're called, when they're executed, the system sets up the this keyword to refer to the specific triangle that that method is supposed to be working with, and the specific triangle that that constructor is supposed to be initializing. That way, in our code, whenever we need to get to the field of the quote-unquote current object, or this object, right, we can use the this keyword as a reference to the triangle that we're trying to work with. The job of the constructor is to initialize the fields, and so that's what this constructor does. It says, going through the this keyword to get to the triangle I'm trying to initialize, the current triangle, this.ax, right, is x1, and this.ay is y1. So I'm taking the information passed in as parameter values, and now I am copying that information as appropriate into the fields of my new triangle that I've just created. Then when the constructor is done setting up the new triangle, it doesn't need a return, it just stops, right? Because we know the constructor's job is to construct the new triangle. And so if we look at how we might use this in our application, going back to our application, remember here's where we read in from our input our 6 numbers, right? So now we can actually take those 6 numbers and create a new triangle, right? Because we have a definition of a triangle as being 6 field names, 6 fields that are doubles, and we have a constructor for taking in that information and initializing it all, right? And so in my application, I've read in my 6 numbers, and they happen to be called AX, AY, BX, BY, but that's just coincidence. The fact that the field names happen to match the local variable names I used in order to read in the information, that's just coincidence. I could have used any names here, right? But once I have the information, I can pass it to my triangle constructor using the new operator, right? So new, that creates the new object. Triangle, that tells me what kind of object to create. And then information to pass to the constructor that tells me, right, what information is passed into the constructor's parameters. And then the constructor, right, then fills the fields of that particular new triangle with the appropriate information. And the result of all of that, right, the result of this expression here will be a reference to that new object fully constructed and initialized on the heap that I can now refer to as T, right? And if we want to visualize what that looks like in memory, right? we can kind of imagine that we are somewhere in a program and we come to this code, triangle t equals new triangle, and then these values, right? So here I have my stack. I'm kind of representing it kind of as a stack, right? And so I'm just imagining this is part of some program. Presumably the very first call frame is main, and then maybe it went somewhere else, and then it maybe went somewhere else. But at some point we called new triangle. So what does that mean? Well, just like a method creates a new call frame and pushes it on the stack, we're going to do the same thing here. We're going to create a new call frame for our constructor and push it on the stack, right? Now the new keyword will have created the structure in memory, right? So we have it allocated, right? The other thing that happens is that when my constructor starts to execute, this keyword, it's a name like, the parameter names like local variable names, but it's set up by the new keyword, by the fact that I'm constructing a new triangle. So that part is set up by Java to say, you're constructing a specific triangle, you're constructing this triangle. So this keyword gets set up to be my empty structure. I passed it values, 1.2, 3.4, 6.0. Those were parameter names, so we know where parameter names go. Those go on our call frame too, right? They act like local variables. So those are x1 through y3. Those are the values that came from my parameters. And now my constructor is ready to do its job, right? And if we look at what the first line of the constructor is, right? The first line of the constructor is going to be the line here. This.ax equals x1. So what does that look like in memory? Right? In memory, when we get to that line, right? This.ax equals x1, right? This.ax, that's set, that's that reference. So now lets me get to that object. Dots, that dereferences that reference. It basically says look into that object. Look for a field called ax, so this.ax. That's that field inside that particular triangle equals x1. x1 was passed in as a parameter, and so I've copied the value 1.2 to that field. And then the remaining lines of the constructor are basically initializing that triangle until now I have my fully initialized triangle. All right. The same thing is going to happen for instance methods once we start to define them, which we will in a second. The idea behind instance methods is a method defined for a specific triangle, for a specific instance, right? And when we call instance methods, again, this keyword gets set up to be the particular reference we went through in order to call that method, right? So this keyword is very useful inside a constructor or inside a method to refer to the current object, right? Whatever object I'm supposed to be working with and manipulating or otherwise is the current object, right? The object whose reference was used in order to get to this method. And often I need this keyword in order to get to those fields values in order to be able to use them. It turns out that those field names, right? Like what happens when we encounter a name inside a method? Well, we look on our call frame and we try to find that name, in our list of names that we know about that are in scope in our call frame, right? So usually, if we use a name that has not been declared as a parameter or as a local variable, that's an error, right? That's a problem. That name is not in scope. There is no corresponding name in our call frame. So usually, if we used a name in a method that was not declared as a local variable or parameter, the program wouldn't compile. But Java's pretty smart, right? And it basically says, look, if you're using a name inside a method, inside an instance method or a constructor, and that name does not correspond to any local variable or parameter name that is in scope, at the time, right, at the point where I need it, right, then I'm going to check one more place. I'm going to say, well, maybe it's really a field name for the current object. So if there's a field that I can access through the this pointer that has that name, that's what I'll understand that name to be referring to. So as long as there's not a local variable name or a parameter name that happens to have the same name as the field names of the current object, you can use the field names of the current object as if they were local variables. You just use their names without having to say this dot and then field name. So this is often implied. So wherever, right, and so we can rewrite that code for the constructor relying on that in the following way, right? So the code used to look like this, right, where we had these names came in as parameter names, x1, y1, x2, y2, x3, y3, and then I use those values in order to initialize these fields, and those fields I access through the this keyword, that's the current triangle I'm initializing, dot, and then the field name, and that's how I was able to provide the appropriate value, copy the appropriate value into the appropriate field, right? But you'll notice that there is no AX local variable, there is no AX parameter name, and because of that, I didn't actually have to say this.ax. I could have just said AX. The compiler will figure it out, because it'll get to AX and it'll say, well, there's no local variable named AX, there's no parameter named AX, but there is a field of the current object, this.ax, that's defined, so it'll understand it to be that field. So as long as there's no name conflict, you can use the field names directly, and the this is implied. And if we took that to, if we did that for all of them, it would look something more like this, right? Where we have, AX equals x1, AY equals y1. All of these things on the left-hand side are really the same as this.ax. Right? Now, as soon as there is a problem, right? Like as soon as, let's say I rename this variable not x1, but ax, right? Now I've got a problem, right? Because now I have a parameter name called ax. And so when I get to this line of code, it's a parameter named ax, so that's what you must mean. So this would be taking this parameter ax and setting it right back to itself. It doesn't make any sense, right? The left-hand side, I also have a field named ax, but I can't get to it because I have a parameter named ax, and that takes precedence, right? If there is a parameter name, if there is a local variable name, then that's what the compiler thinks ax refers to. So if this was the case, then I would have to do this, right? I would have to explicitly say this.ax, go through the this pointer to the ax field. That field equals ax, this parameter, right? All right. Okay. So now we can create new triangles. The next part of this is to define what those triangles can do. So instead of having a library of triangle-related functions, each of which requires the programmer to provide all the information about the triangle or this to those functions and then get back an answer, instead we're going to define those functions as part of being a triangle, so that every triangle can say, I can calculate whatever about myself, right? I can calculate my area. I can calculate my perimeter. I can calculate my category. I don't need you to give me the information that is part of the triangle, because that is in my fields. That's part of me. That's part of the triangle, right? You may have to give me other information, things that are not part of me that you need for the method to work. But the triangle part, that I already have. That's the structure. That's the object. And now I can define instance methods that work or that operate in the context of a particular instance of a triangle. So I can ask a specific triangle, what's your area? I can ask a specific triangle, what's your perimeter, right? And so I define those methods in the triangle class as instance methods. The only difference between an instance method and a class method is an instance method does not have the keyword static, but it does have the keyword, like in its declaration, but it will have the keyword this defined in its body. Because in order to call an instance method, I have to first start with a reference to a triangle, and then say dot, and then the method name. It's that left-hand part of the dot. That is what's determining which triangle I'm going to be referring to, that I'm going to be working with. And it is the value of that reference, which is the value of this inside the method when it executes. All right. So to kind of demonstrate this, let's define some triangle-related methods. So here's my triangle, and here's my constructor for creating new triangles. One thing I might want a triangle to be able to do is to report its category, right? So in the old code, I had something that looked like, like this. Static triangle category, you give me 6 numbers, I give you back a string. In the new way of doing things, I say, go create a triangle out of 6 numbers, and then you can ask that triangle, what's your category? Right? I don't have to provide the 6 numbers, they're already there. Right? They're already part of the triangle I'm working with. So when I get a triangle and I say dot category, I'm saying that particular triangle, go call this instance method in the context of that particular triangle. Right? So inside category, this will refer to whatever triangle I've asked for its category. And now I can calculate, using the field values of this triangle, the appropriate category and return it. Right? So the code's pretty much the same. It's still calculating the side distances. In this case, I've pulled this instance method as part of triangle now. So point distance was left behind in triangle area app. So I need to, because it's in a different class, I have to use a fully qualified name, but that's OK. Right. And so I say side AB, side BC, side C. I basically are using the values of my fields in order to calculate my sides, compare them, and return my category. Same thing with area, right? I can now have every triangle calculate its own area. What this allows me to do is to rewrite my application so that now, after reading in my 6 numbers, I can create my new triangle, and now I can work with that triangle because it has behavior. It has methods, instance methods, that will tell me things and calculate things with respect to that specific triangle. So once I've created that triangle as triangle T, now I can say, T, please give me your category, T.category. Right? Call the category method in the context of this of the triangle T. So this triangle is this triangle T, and then we go to category and start to execute there, and all these fields come from this triangle, this.ax, this.ay. Similarly, I can ask that triangle for its area, right? And slowly but surely, we're starting to transform our original program into one that is making use of objects as structures, right, as appropriate. Right. OK, so if we look inside area and category, we can see that we actually end up calculating sides a lot, right? So side AB, side BC, side CA. That's something that we can turn into instance methods if we want, right? We can say, every triangle can tell me what its side AB is and what its side BC is. And I can use that internally as well. So I might do something like this, where I now have side AB, right, returns the point distance between the AX and AY and the BX and the BY, and side BC and side CA. And so I've basically created instance methods for saying, give me a triangle, and I can calculate what it thinks its AB side is. Give me a triangle, and I can calculate what its BC side is. In this case here, I'm still using point distance as a static helper function. The only thing I've done is I've just pulled it over into this into the triangle class, so I didn't have to use a fully qualified name. But now that I have these instance methods, I can use them in other instance methods. So instance methods can use other instance methods for the same triangle, right? So for the category, I can just call side AB. That's the same thing as calling this dot side AB, right? So if you're in an instance method already and this is already defined, then you can call an instance method on the same object just by using the name of the method. It will know that, it's the same this, right? You can also do it explicitly if you'd like. So this dot side AB would work just as well, but often we'd leave the this dot off because it's implied, right? All right. If we look at triangle, we should be able to see an opportunity to kind of do this exercise all over again, right? Just like we said, those 6 numbers represent a triangle, and we don't want to have to remember that, we need 6 in what order and which ones are which, and and why. We want a new abstraction that represents a triangle, and we want these 6 numbers to be fields of that triangle, and then we want to be able to define instance methods on that triangle for working with those 6 numbers as a triangle, and not have to worry about the details in the program that I'm writing, right? Same thing here, right? These fields aren't just, it's not AX and AY aren't 2 random numbers. They go together, right? That AX goes with that AY. It doesn't go with the BX. It doesn't go with the BY. And there's a meaning. There's a relationship between those 2 values. In fact, that AX and that AY represent a point, right? And so we could go through this entire exercise all over again and say, what I really want is a point abstraction, like this, where I have points. And a point is made out of an x coordinate and a y coordinate. To create a new point, I have a constructor that says, you give me an x and y value, and I will fill my x and y fields with those values to create a new point. You can see here, I use the same names for my parameter names as my field names, which is why I can't rely on the implicit this. I have to be explicit on this side, right? I did that on purpose just to show you. So that's how I create a new point. And then I can say, points are going to have things that they can do, right? And one of the things that I want to be able to do with one point is to calculate its distance to another point. And so we can do that as well. We can say, I'm going to have an instance method. We know it's an instance method because there's no static that says distance to, and then the parameter will be, you give me some other point. And I will calculate the distance between the current point, this point, and the other point, the one that you passed in. Right? Even though there happen to be objects of the same type, you can only have one this. Right? I have to be working in the context of a particular point. And so if I need the values or the data from some other point, then that has to be passed in as part of what gets passed into to my method. So the distance to method of a particular point says you give me a different point, and I will calculate the correct distance. X by itself, right? There's no parameter named X. There's no local variable named X. So this X refers to this X, right? Is literally this dot X is the same thing. I can say just X because there's no confusion. So I know that that refers to the field of the current point. In order to get to the other point's X, that I have to go through this other point reference, right? Just like to get to the length field of an array, you start with an array reference and then you say dot length. So in order to get to the X field of this other point, I can't just say X because that will give me the X field of this point. So to get to the X field of the other point, I have to go through the reference given to me and get to its X field. But now that I have this handy-dandy point abstraction that I can rewrite triangle so that, a triangle isn't 6 numbers, it's 3 points. You give me 3 points, and I'll store them in my fields, point A, point B, and point C. And now I can say, side AB, that's just the A point's distance to the B point. So I'm using the distance to method of my A point to calculate the distance to the B point. And so I can rewrite all of these methods now using point as an abstraction and point with its own instance methods. So point takes two doubles and pushes them together turns them into a point and gives us a distance 2 method in order to calculate distances to other points. Triangle takes 3 points, puts them together into 3 fields as a triangle, and then provides things like category and area and side AB, side BC, etc., in order to calculate things about the triangle. And then my actual program now works, right, by saying, oh, take 2 values, turn them into a point, take 3 points, turn them into a triangle, and now work with that triangle, right? All right, so all of this is basically to get across the idea of taking data, putting it together as a set of fields that are part of an object, and then defining operations and methods on that object. That essentially is a data structure, and starting on Thursday, we'll start to talk about data structures more formally and using Java to program them.